Now, what we want to talk about is when we have a capacitor in series with a resistor. Let's make that connection a little bit better. And a battery. Okay, now we're going to assume that at time equals 0, right when this connection is made, the charge on the capacitor is equal to 0. Okay, so we're going to assume the capacitor is initially uncharged. And we're going to give our battery a voltage source V0. And this would be the plus terminal. And that means we're going to have a potential across the resistor of VR. And we would have a potential across the capacitor of VC. Right? Now, by the loop rule, we would have, at all times, this relationship must be satisfied. Okay? At all times, this relationship must be satisfied. Now, what are we wanting to understand here? What are we wanting to determine? Well, if the capacitor is uncharged initially, there's several questions we can ask. Number one, what is the current as a function of time? Right? As the capacitor charges, that will alter how the current flows through the circuit, and as a result, the current will not be a steady value. So how does the current change with time? If the current doesn't change, or if the current isn't static, rather, if the current changes with time, then that means that the voltage across the resistor is also going to be a function of time. And by that same token, the voltage across the capacitor will be a function of time. And we can also ask, if we want to, what is the charge on the capacitor going to be as a function of time? Okay? And it all starts with this equation, with the loop rule. Okay? It all starts with the loop rule. Now, how can we start to answer these questions? We're going to do something that may be slightly counterintuitive. Okay? We're going to do something that may be slightly counterintuitive, and we're going to differentiate this equation with respect to time. Time does not explicitly appear yet in here. Now, we're arguing that these values, VR, VC, the current, and so on, shouldn't be static, so they should be functions of time, but time does not appear directly in the loop rule as is. So here's what we do. Differentiate the loop rule with respect to time. And when you apply the derivative to the voltage of the battery, that goes away because the voltage of the battery is constant. And then you get to take the derivative of the voltage of the resistor and the derivative of the voltage of the capacitor. Okay? But remember that VR is equal to IR, so this term is the same thing as taking the time derivative of IR, which is, R is constant, so you don't need to take the derivative of that. So this is just di dt times R. And likewise, from the definition of capacitance, this is going to be taking the time derivative of Q over C. And so, once again, C is also constant, so this is going to be the time derivative of the charge times 1 over c. But the time derivative of the charge is just the current. So this is I over c. Okay? So at the end of the day, for the loop rule, we would have 0 equals R di dt plus I over c. Mathematicians might write it like this. And this kind of puts it in the form of a coefficient times the derivative of a function plus a coefficient times the function. And this is how a lot of differential equations are written down. And so, what do we do with this? Okay, well, what we can do is we set both sides equal to each other with the minus sign. So what we do is let's move this over to this side. So we would get negative 1 over c times I. And that means R di dt is equal to negative 1 over ci. Okay? And now I've got a differential of I, and I have an I, so let's group those together. And then let's put everything else on the other side. And so when I do that, I'm going to get di over I is equal to negative dt over rc. Ooh, there's that rc again. So here the time constant comes back into play. So remember that rc is the same thing as tau, and this is the time constant. Okay, so we've got di over I is equal to negative dt over tau. Okay, and now we're going to integrate, and we're going to do the same thing we did in the previous video, and we're going to use the initial condition that if you look at this circuit as is, okay, when the current initially starts to flow, when the switch is just flipped, okay, when the current just starts to flow, the capacitor acts like it's not there because charge is being put on one of the plates and being drawn off at the other plate just at the rate that V equals IR would push the current. And so as a result, the initial current at time equals 0 is just going to be V naught over R at t equals 0. So this is our initial condition. Okay. So, and we can label this as I naught. Okay. So that's the maximum amount of current that would flow. And so we're going to get ln of I is equal to negative 1 over tau. The integral of dt is t plus our integration constant. And when you take the exponential of both sides, you get the current is equal to e to the negative t over tau plus k, which turns into e to the negative t over tau times e to the k. And now we can use that initial condition at t equals 0, I equals I naught. Okay, so I naught is equal to e to the 0 times this quantity, and let's once again go ahead and call it b. And so that means that I naught is equal to b. because e to the 0 is 1. So I naught is b. So the exponential of the integration constant once again represents the total current, or the maximum current, I should say. So with that in mind, our current as a function of time looks like this, where B is now once again the maximum current. So we have answered the first of our questions. Okay? We have answered the first of the questions, and that is, what is the current? So just as in the discharging case, the charging case, the current still is exponentially decaying. In one case, it's because the plates on the capacitor were losing charge, and as they lost charge, there was less charge to move, and the potential across the plates diminished, decreasing the electric field in the wires. And what's happening here is that as charge gathers on the plates, there is a stronger potential across the capacitor, and that diminishes the potential across the resistor, and that causes the total amount of charge that can flow through the resistor to diminish. Okay, so here we've got an exponentially decaying current. Now, what was the next one we wanted to look at? We also wanted to see what is the potential across the resistor. So this is A. B, what is the potential across the resistor? Well, the potential across the resistor is just going to be IR. So VR is going to just be I naught e to the negative t over tau times R, or I naught R e to the negative t over tau. But from here, I naught R is equal to V naught. So initially, what this equation is telling you, initially, all of the voltage from the battery appears across the resistor. And that's because there's no charge on the plates yet, so they don't have any potential across the plates yet. And as a result, all of the potential appears across the resistor, and the potential across the resistor exponentially decays. What about the potential across the capacitor? Well, the easiest way to get this is to go back to the loop rule and say, well, if the voltage across the resistor and capacitor have to add up to the battery, then it stands to reason that the voltage across the capacitor must be the voltage of the battery minus that of the resistor. So we have this condition, and this is going to be V0 minus B0 e to the negative t over tau. And if I factor out my V0s, this is V0 times 1 minus e to the negative t over tau. Okay. Now, here's an important point. Here is an important point. The voltage across the resistor exponentially decays. The voltage across the capacitor does not exponentially grow. Okay, this is not exponential growth. If I plot as a function of time if I plot the potential, then the potential of the, let's use red for the voltage across the resistor. So the voltage across the resistor is going to start out at some value V naught, and it's going to exponentially decay, and eventually it will approach zero. Now that's not a terribly great exponential curve, but you get the picture. And so V naught is a constant value, and while that is decreasing like that, if I use purple for the um, voltage across the capacitor, it starts at zero and grows something like this. And it will asymptotically approach that V naught value. Okay, so this is not exponential growth. Exponential growth would grow like this without bound. Okay, so it's not doing that. So it's not exponential growth. If you just visually look at it, it almost looks logarithmic. It's not logarithmic, but it's closer to logarithmic than it is to anything else. Okay, um, and so just beware that just because the voltage across the resistor exponentially decays, the voltage across the capacitor does not exponentially grow. Okay, it grows like this. And for part D, what about the charge as a function of time? Well, now that you've got the uh, voltage of the capacitor, you can say, remember that the relationship here is that Q equals CV. And so, as a result, Q is going to equal C times V naught 1 minus e to the negative t over tau. And C times V naught is just the total amount of charge that the plates can have, Q naught. So Q is going to grow as Q naught times 1 minus e to the negative t over tau. And that is the capacitor and resistor in series when the capacitor is charging. Okay? I hope that you have found this helpful, and we will see you when we talk about magnetism.